Hello everyone. Inside this video we're going to be taking a jab at a momentum problem. However, before we begin this problem, I would like to encourage everybody to go and wash your hands before you start watching the rest of this video, because sometimes when I'm watching a video and I'm really focused on it, I subconsciously touch my face. And in light of the recent corona epidemic or pandemic, that is something that we want to avoid. So go ahead and wash your hands for about 20 seconds, then rinse, then wash your hands again for another 20 seconds, then dry them off and come back. So if you do touch your face, you lower the risk of exposure. Okay, so let's begin. Currently, we have a child in a boat, and this child throws a 10-kilogram package out of the boat horizontally with a velocity of 10 meters per second. Calculate the velocity of the boat immediately after it was initially at rest. So this is the exact wording of the question, but when they say immediately after, they mean immediately after the package is thrown out of the boat. So they're telling you now that the mass of the child and the boat is 79 kilograms. So here, this is how I usually like to start my problem. I always write out all the variables that I'm given, and I usually go from there. So here I have mass of B plus C, which is mass of the boat plus mass of the child, which is, and I made a mistake, that should actually be 79 kilograms. Here I have mass of the box, which is 10 kilograms. And here, if I don't have anything written there, I'm going to denote these as the initial velocities. So I have the initial velocity of the boat and the initial velocity of the boat plus the child. Sorry, this is supposed to be initial velocity of the box. So initially, everything is at rest. The child is sitting in the boat with the box in his hand, and for some strange reason, he decides to toss the box out horizontally. Now, by conservation of momentum, momentum must be conserved. So it's better if I actually work it out and you can actually see what happens. But first, I'll draw a little diagram. So we'll call this thing the boat. This is the child. Horrible drawing. Luckily, you don't have to be an artist in physics. So right now, both of them are at rest. Okay, this is before the collision. And sometimes I like to say event because it's not, when you intuitively, when you think of a collision, you wouldn't think of something like this. And here, this is what happens after the event. So here, the child throws the package. This is the package flying off in that direction. We're gonna let that be to the right. This package has some velocity there. However, what's gonna happen here is they're gonna move in the opposite direction because momentum must be conserved. So using the conservation of momentum, saying that momentum must be conserved, what this says is that the momentum is denoted by P. So it says total initial momentum must equal to total final momentum. Okay? Initial, final. So initially at the beginning of the problem, you look at how many objects are you dealing with inside this problem. This can be extended to 2 objects, 3 objects, and an infinite amount of objects. You could extend this to a system of particles, which is what they actually do when they're dealing with really, really, really large systems. But that's beyond the scope of this problem. So here, how many objects do I have? And momentum is defined as the mass of an object times its velocity. So I have 2 objects at the beginning. I have the momentum of the box times the velocity of the box. Sorry, the mass of the box times the mass of the boat plus the child plus the initial velocity of the boat plus the child. And this must be equal to the velocity after, which again is, well, the momentum after, which is the mass of the box, which stays the same, times v prime, which is the final velocity of the box. Final velocity of the box plus mass of the box plus the child times velocity prime of the box plus the child. Now, since initially they're at rest, this and this is zero, the initial velocity of the box and the initial velocity of the boat and the child, since they're all together, they're all together, you could think of them as stuck together. All their velocity is the same. They're moving with the same velocity. So if one is at rest at the beginning, without any further information, we can conclude that the entire thing is at rest. So this goes to zero because the mass here times zero plus the mass here times zero means that this entire thing is equal to zero. So now we're just left with the mass of the box times the final velocity of the box plus the mass of the box plus the child times the velocity, well, the final velocity of the box plus the child. And this is what I want to find. And luckily for me, I know that the mass of the box is, I know what the final velocity of the box is, and I also know the mass of the boat plus the child. So with a bit of algebra, I can solve for this. So the final velocity of the box is equal to minus the mass of the box times the final velocity of the box. I hope I didn't say box over here. I see that I'm mixing up box plus child. And this entire thing is divided by the mass of the box plus the child. And here, these are all things that I know, so I'm going to keep that negative there. And the mass of the box is 10. And the velocity of the box, I actually wrote down the wrong thing, but for the sake of the question, it doesn't matter. So the mass of the box is 10, and the velocity of the box is also 10. The mass of the box was supposed to be different, but it's still going to work out. It's still going to work out to something that makes sense. And here, divided by the mass of the box plus the mass of the boat plus the child. And this is 79 kilograms. So this actually ends up working out to be negative 100 over 79. And when we work this out, we end up with 1.266, negative 1.266 meters per second. Now, you'll notice that there's a negative there, and that negative tells us something very important. Since I defined my coordinate axis, I said over here that the velocity of the box is going that way, to the right. And I said over here that the velocity of the boat and the child are going in the opposite direction. Notice that I defined the velocity of my box right here to be positive. And momentum is a vector, and momentum is a vector because velocity is a vector, meaning that direction is very important. So when you get the negative signs on your velocity, what that tells you is the direction that it's going. And since we're only operating in one dimension, we're going left and right. Whenever we deal with momentum, we're either going to get signs that are positive or signs that are negative, and all of these have a meaning to it. In this particular case, the 1.266 meters per second is to the left. The magnitude of this velocity is 1.266, but the direction is in the negative direction, or to the left. So the mass of the box was actually written down to be 5.3 kilograms, but I made a mistake. But it's just something that you can switch right here. Of course, you're going to get a much lower number than this, but again, the principle still holds. The child is in the boat, and the child throws the box out of the boat horizontally, and because momentum has to be conserved, the child goes backward, or the child recoils. So if you've ever thrown anything and you were maybe on roller skates, you'd notice that you actually move in the opposite direction. and that holds because momentum must be conserved. So this was a very nice example of that, and we're going to operate further with momentum, so hopefully you get a better understanding of the situations.